Okay, our next set of questions are going to be looking at our sex-linked traits. Remember, with our sex-linked traits, we need to look at not just the alleles for the genes, but also the chromosomes X and Y. And you only do this if the trait is sex-linked. If it's not sex-linked, do not use X's and Y's. I emphasize that every year, and every year I get students trying to force the X's and Y's into a non-sex linked trait. So, to start with, color blindness, we're representing it with the letters CB, and of course we need to indicate that it's on the X chromosome. So we're going to look at how do we write the genotypes for different individuals. So remember, this would be their genetic combinations. What would the genotype for a normal male be? Well, if he's a normal male, he has an X and a Y chromosome. If he can see colors, that means he has the dominant copy of the gene. So we would write a capital CB superscript to the X. All right, a normal female, and we're going to assume that this normal female is not a carrier. So she has 2 X's. If she's not a carrier, that means she has capital CB superscript on each of those X's to indicate that both of her X chromosomes have the dominant allele. Now, a colorblind male. He's a male, so we have to put an X and a Y. And then on the X chromosome, he's going to have the recessive allele because he is colorblind. For a colorblind female, well, she's going to have 2 X's, and to be colorblind, she has to have the recessive genes on both of her X chromosomes. And then a carrier female, again, she's going to have 2 X's, and she's going to be a carrier. So that means she has the dominant allele on one X chromosome and the recessive allele on the other. Okay. So see how for each of these different types of individuals, we've notated which allele of the gene they have and which chromosomes they have. Now, a lot of students want to try to put that CB on the Y chromosome too. Y chromosomes do not have that gene. That is why males are more susceptible to sex-linked traits, to recessive sex-linked traits. Because if they get a recessive copy, they don't even have a chance of getting a second copy for that gene that might be dominant because the Y chromosome doesn't have that gene. Okay. Now, we're going to stay with color blindness. Okay. So color blindness is our sex-linked trait. And Josie has normal vision, but her father is red-green colorblind. And Joe has normal vision. What is the probability that Josie and Joe will have a child that is colorblind? Okay. So, and what is the probability that their sons will be colorblind? What is the probability that their daughters will be colorblind? So we're going to come down here, and so I have some room to work. And Josie has normal vision. So I'm having a hard time watching in the camera and writing on the paper so I can see what I'm doing. So Josie has normal vision. So we know she's got one dominant copy of the gene. And her father is colorblind. Since men only have one X chromosome, that means he gave Josie his X chromosome with the gene for color blindness on it, the recessive copy of the gene. And Jose, or Joe, has normal vision. So that means he has an X and a Y, and on his X he has a dominant copy of the gene. So if we do our cross, draw out our Punnett square, okay. We're going to do Josie across the top. We're going to do Joe down the side, and then we're going to do our cross. So in our first square we have X with capital CB, X capital CB, second square, X capital CB, X lowercase cb. Here we have X capital CB, Y, X lowercase cb, Y. All right. So we filled out our Punnett square. So our first question was, what is the probability that Josie and Joe will have a child that is colorblind? Well, if we look at this child's not colorblind, this child's not colorblind, this child is not colorblind, but this one is. So that's 1 out of 4 will be colorblind. 25% chance they will have a child with colorblindness. Now the second question is, what is the probability that their sons will be colorblind? So now we're only looking at the boys. So we're only looking at these bottom 2 squares. And 1 out of 2 boys or 50%, put the 0 in there, will be colorblind. The probability that their daughters will be colorblind. If we look there, both their daughters have at least 1 dominant copy. So 0 girls or 0%, 0 out of 2 or 0% of the girls will be colorblind. Okay. Now, in these next questions, we're still staying with our color blindness in humans. Can a normal vision male produce a daughter that is colorblind? Well, a normal vision male has that genotype. So he only has a dominant copy of the gene. So no, he cannot have a daughter that is colorblind, because he will always give the dominant copy of the gene to his daughter, so every one of his daughters will have at least 1 dominant copy of the gene and thus will be able to see colors. Can a normal vision male produce a son that is colorblind? Well, what do we know here? Males give their Y chromosome to their sons. So this is the chromosome they're giving to their sons. That plays no role in whether or not their sons will be colorblind. So that all depends on the mother. But yes, a normal vision male can have a colorblind son if the woman he is having his child with is colorblind or a carrier for colorblindness. How could we get a colorblind female? Well, in this case, Dad has to be colorblind. Mom would have to be colorblind or a carrier for colorblindness. Because the daughter has to inherit 2 recessive alleles, 1 from her dad, 1 from her mom. Now on this next one, we're looking at hemophilia. So hemophilia is a disease caused by the recessive allele X lowercase h, found on the X chromosome, A normal man marries a woman who is heterozygous for hemophilia. Give the genotype possible offspring. Okay, so if we look here, we've got Dad has a dominant copy of the gene, so he has the X chromosome with a capital H on it. Mom is a carrier, so she has X capital H and X lowercase h. So if we do our cross, we're going to go XH, X lowercase h, X uppercase h, and a Y. So we'll go XH, 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 lowercase h, X uppercase h, Y, X lowercase h, Y. So we want to give genotypes and phenotypes for our possible offsprings. Okay, 75% chance normal for hemophilia. 25% chance hemophilia. And these are our phenotypes. Our genotypes. Let me shift this a little bit. 25% homozygous dominant female. 25% heterozygous. 25% male who is hemizygous for the dominant trait, and 25% chance male who is hemizygous for the recessive trait. Remember, genotypes are actual genes and phenotypes are our expressions of those genes. Okay.